Hello, welcome to this stream, guys. In this stream we are going to continue building the VM translator that we were building in the last stream. So in the last stream we created this parser class and we created a code class as well, specifically code writer class. So this parser class passes the instructions and gives us the types and the different arguments, and the code writer class gives different methods which gives us the translated instructions. So yesterday we wrote this, not yesterday, day before yesterday exactly, we wrote this method write arithmetic to translate the arithmetic instructions. So let's see. These are the equivalent assembly instructions for the arithmetic instructions of the VM code. I'm not sure if they're correct or not. We'll see later on when we try to test the programs. But before we try testing it, I think we should write this method as well, write push pop. So we'll do just that right now. We'll start with this method push pop. So this method will give us the instructions for push pop instructions. Let's write a method. We'll name it write push pop. Okay, let me see if we were giving any arguments to this arithmetic method or not. Yeah, we were passing the parser argument, so we'll do the same for write push pop. Let's pass parser. Damn, I can't type. Okay, so after passing the parser, what we are doing? If parser.type is not equal to C arithmetic, we were simply returning. So we'll do the same thing for write push pop. If parser but in this case we will return back if parser.type is not equal to, let's see, push or pop. We have two different types of instructions, right? C arithmetic as well as, let's check the parser. Yeah, we have push, C push and C pop. So we'll use this one. C push. Also we need or. Parser.type not equal to C pop. So if the parse instruction is not of type C push or C pop, then we will simply return. But if it is a type of C push and C pop, what do we need to do? Alright, so the output file, that assembly code. All right, so we need to translate that push pop instruction to their equivalent assembly code. So let's check the machine language. This is how the push and pop instructions will look like inside the VM code. Push segment I, pop segment I. Probably we will have to keep condition so that we can distinguish between different segments, because let's see, this push segment, push instruction takes all of the segments, so yeah, but this pop doesn't take all of the segments. It takes let's say it leaves out this constant because it doesn't make sense to pop constant, because the constant segment doesn't really exist. Alright, so the machine code for push and pop for these 4 segments, local argument, this and that, will be similar. So yeah, are implemented precisely the same way. So let's see how we should do this. This is the pseudocode for constant, for push constant statement. So let's see how this differs from the pseudocode of this 4 segments. So in here we were selecting a base pointer and segment pointer plus this index, and this will be the address, and whatever is there at the address, we are storing it inside this take pointer for push instruction, and we are incrementing the stack pointer. But in case of constant, we are simply getting this I value and pushing it on the top of stack and incrementing the stack, because you see we don't need to point to any particular segment because the segment for constant doesn't really exist. Okay, so this is for the constant, and for static, okay, the instructions for static will be different as well, because yeah, we'll see when we have to implement this one. What do we have after that? We have this temp. So in case of temp, this is almost similar to the 4 segments that we previously saw, which were local argument, this and that. But the only thing which is different in this case is, instead of a particular segment address, it will always be 5 in this case. So yeah, after that, the temp, what do we have? We have pointer. This will be the pseudocode for pointer, and this looks somewhat similar to the constant. So you know what we can do, as these statements are bundled together according to this segment, we'll keep conditions or implement conditions for this different segments. So, and inside that we will see which instruction do we have, if we have a push or a pop, and accordingly we will write the assembly code. So let's try to write the instructions for this segment, this 4 segments, local argument, this and that. So to do that, first we'll see if the segment, so to get the segment we can call parser dot arg1, because arg1 is segment and arg2 is, I guess, yeah, arg2 is the integer part. So we'll call arg1 and check if equal to, not segment, either local or if it is, what we will be having, argument, local argument this, that. if the argument 1 is either of these 4 types, then what we will do, before we write the condition, let's create this type of strings for push pop operations as well. So we'll be writing the strings, the comments first. So let's see, if we have push segment I, where segment is either of type local, argument this, that, and the pseudocode will look like, we'll have we don't need to write the pseudocode right now because we already have it inside the slide. So let's just write the assembly code directly. So first we need an address pointer to store the segment pointer. So this segment pointer will be this one, either local or this or that in this case. So first we'll just write it for local. So how are we going to do that? We will first get segment pointer, so let's write it down for local. This will select this memory segment. I'll see them now. And what can we do? Let's see, we'll store it inside data register. This will store the pointer to local segment inside the D. After that, we'll create a new variable, not local, ADDR, and now ADDRE. So now what we can do, M is equal to D plus, wait, but before we do this, we also need this constant inside a particular variable as well. Yeah, let's get I register, I variable, and inside this I variable we need to pass the constant, because this I, how I'm going to pass this constant? Before we get this variable, we need to get this constant. So let's see how we're going to do that. So in this case, we'll be having parser.arg2, which will have this constant value. Now first we will need to store it inside a temporary variable so that we can access it later, and the temporary variable will be I. Okay, let's say the constant is something like this. This is not a variable, this will be what will be passing. So instead of adding this, let me just write arg2, because this arg2 will be having this constant value. This will store the argument 2 inside A. Now we will store it inside the data register. Now we'll select the I and we'll store this value inside this I variable. So now we have I is equal to whatever the constant it is. Now let's see what we can do. First we select the local pointer. This is going to be a bit harder, because let's see what we'll do here is, because we just have 2 registers, therefore the code seems a bit more complicated. We select the local LCL and we store the pointer value inside this data register. Wait, but instead of getting this temporary variable I, what if we just get this address register and store this I value there directly? That will be easier, I guess. So suppose we get this ADDR. Now we store this constant value inside ADDR directly. Now this ADDR already contains this I value. Now all we need to do is get this segment pointer LCL and store the value inside D. After that we'll get this ADDR again, and M is equal to M plus D. So this M already contains I value, and this D will have this LCL pointer value. So now this address variable points to the particular RAM index which was pointed by this I inside the particular segment. In this case we are just concerned with the local segment. Okay, so now what do we need to do? We need to store this value inside the stack. So to do this, let's get this value. First we'll need to get that value which is pointed by this ith index inside this segment. So to get that, first we need to do A is equal to M. So now this A will point to that RAM. After that we can get the value like this, D is equal to M. So now the value is inside the data register. Now we can select the stack pointer and push the value to the top of the stack. So to do this, first we have to do a is equal to m, and now we can do m is equal to d. This will push the value on the top of the stack. Let me check if this is correct. So in case of, yeah, this is correct. Now we have pushed this value, so we have implemented these two codes. Now the only thing remaining is incrementing the stack pointer. So we'll have to get the stack pointer again, and now we can do m is equal to m plus 1. This will be, so this is it for the push local I code, and the commands will be same for argument and this and that. The only thing we'll need to change is this variable. We'll change LCL to arg in case of argument, and this and that in case of this and that. So now let's write the code for pop segment as well. Pop segment I. So the steps up to to this step, it will remain similar, but after this step we need to decrement the stack pointer. So let's cut this and paste it over here. In this case we need to decrement the stack pointer. Now that we have decremented it, instead of getting SP, in this case we'll now need to get the ADDR and do A is equal to M and M is equal to D. But wait, before we do D, we'll have to store something inside D. So let's see, up to this step we are just adding the address of the segment, that particular index of the segment up to this point. And now this D contains wait, I'm confused. Let me go back to push again. So first we are doing first we are getting the arg2 and storing the value inside data D register. After that we get new variable ADDR and store that value inside that variable. After that we get LCL and we do D is equal to M. And so store the value of LCL inside this data register. After that we add that data value to the address variable. So now this address variable contains segment pointer plus I, so it contains the index of that particular segment. After that we do A is equal to M, so this will select that particular a register of that segment, and now we store it inside the data register. After that, we select the stack pointer, do a is equal to m, and store that value inside the m is equal to d. After that, we decrement the stack pointer. So now in this case as well, steps up to this point will remain similar. But well, this is correct. So first we have to decrement the stack pointer. So we do m is equal to m minus 1. After that, we get the address register. Okay, so we don't need to do this. So once we get the stack pointer, we decrement it. And after decrementing it, we'll store d is equal to d. Wait. We'll do a is equal to m, and d is equal to m. So this will give us the value. This will pop the segment, that value from the stack. And now we select the address variable. We do a is equal to m, and now we can do m is equal to d. So yeah, these are the steps for pop segment I. So now we have code for push this 4 segments, push and pop instruction for this 4 segments. So before we continue, let's write it inside a single string. We need to call it push LCL. Yeah, the name is up. Now we'll replace the new line with comma. Yes. Okay, that is it. Okay, this is the string for PushLocal. We need to change this thing, arg variable. So to do that, first we'll have to get the argument constant. So before we write the code, let's save arg1 inside arg1 push arg1. We'll be having argument 1 inside arg1, and arg2 parse arg2 so that it will be easier. So here we'll have to pass that argument. arg2 I hope we can use format strings inside this like that. So this will give us push local assembly code. What else do we need to change? There's nothing, I guess. So let's copy this code and write it for push arg. So I will call it push arg. And in this case, we need to change this pointer. Instead of LCL, we will have arg. Now let's get the string for this. Push this. And here as well, we'll have to change the label. This to this. That. Alright, so we have the assembly code for push local, push argument, push this and push that. Now we need to get the statements or the instruction for pop, and we'll store it inside pop lcl. Replace new line and space with comma. Blank lines, then use percentage to replace all, G continuous voice space. So this is the regex command for white space. Dash s dash plus. Okay, so let's see if it works or not. New line dash s dash plus. Yeah, it works. Right, so we have the instructions for pop LCL as well, and I think we don't need to change anything else. So let's copy this command and write it for push r pop arc. The only thing we need to change is this pointer. This will be arc. Push pop this at this and that. Okay, so we have this assembly code for all of these 4 segments. So let's write the condition for the same. Now, as we have already got arg1 variable, we don't need this. Okay, so let's see what we have to do. If argument 1 is equal to local argument this or that, well, instead of having just one single condition, let's just use different conditions, because we have different commands for all these different conditions anyway. So let me copy the first condition first. If arg1 local and arg2 equal to push, and let's see, we'll just print right now. Push LCL, replace the comma with a new line character. Else if argument 1 is local and argument 2 is pop, we'll do pop LCL. Else if is argument 1 is argument and argument 2 is pop push, then we'll do push arc, and in this case we'll do argument pop then pop arc. Argument 1 is this, then we'll do push this. Or pop that, pop this. If it is pop, if it is that, oh wait, what happened? Change something else. These are for the argument, this is for this is for, wait, I messed up somewhere. So this and push, then push this, pop this, that push that. Pop that. Let me recheck it. So if the argument 1 is local and push, then we do push local. If it is pop, pop local. Argument push and push arg, pop arg. This push this, pop this, and push that, pop that. Yeah, it is correct. Okay, so let's continue writing the assembly code for other segments as well. So after push and pop segment, we have this constant segment. So this is the pseudo code for constant. It is very easy comparatively. So let's write it for so the instruction is push constant I, and what we will do, we'll first need to get this I. So we'll do the same thing, we'll get the argument 2, store it inside the data register, we are at slide 72. So we already have the hack assembly code for this push constant. This is what I was going to do anyway. Let's copy it directly. So after getting this, arg2 is constant in this case, I. Now we need to get the stack pointer. After getting the stack pointer, we need to store that constant value at the stack. So to store it, first we'll do a is equal to m, and m is equal to d. So d contains the value of arg2, and after that we'll increment the stack pointer. Okay, this is it for push constant. Push const is equal to Okay, so we have the instructions for push constant and as well, and we don't have pop constant, so we don't need to take care of it. Let's go back to slide 71. So we have implemented this assembly code for push constant. Now we have static. Okay, so the code for static will be somewhat different. And in case of static, also we'll have push and pop static. So let's see how it will look like. So if we have an instruction like pop static 5, the equivalent assembly code will look like this. We first get a variable, and the name of the variable will be like this. It will start with the file name. Okay, so we'll have to get the file name as well first, and after that, after dot and the constant which we are storing. So this will be the variable name, and m is equal to d, so d will be the popped value. And what if we have pushed? Okay, instead of just mumbling about it, let me write. So let's say we have push static 5. What do we need to do in this case? First we need to get the value of static 5 and push it inside the stack, on top of the stack. So we'll do something like this. O will be the name 5. We'll do d is equal to m. So now this d contains the value. Now we need to push it on the top of stack. So we'll get the stack pointer, and a is equal to m, and m is equal to d. So after m is equal to d, now we have pushed the value of 4.5 on the top of stack. Oh wait, instead of writing this, I will have to write I, because we don't provide the value directly. So what we'll do afterward is it the same thing, arg2 Okay, so now this is somewhat difficult. Alright, it is not difficult. We have to provide this I over here. So instead of I, will provide arg2 in our case. This will select that that memory, and this will get the data d is equal to m. After that, we select the stack pointer, do a is equal to m, and after that we do m is equal to t. So now we have the value at the top of the stack. After that, we need to increment the stack pointer. M is equal to m plus, this looks somewhat similar to push constant one. Let's write the pseudocode for pop static I. So in case of pop, first we'll get the value from the stack. So first we'll select the stack pointer and do a is equal to m wait, we'll first have to decrement the stack pointer, right, to pop the value. So we'll do m is equal to m minus 1 first. That's what we are doing previously as well, right? So after we have decremented it, we'll do a is equal to m and d is equal to m, so that we have the value of the top of the stack. Now we'll select this O arg2, and instead of doing d is equal to m, we'll do m is equal to t, so that we have the value of that popped thing inside this, and we don't need to carry out this remaining steps. So let's walk through it again. First we are selecting the stack pointer and decrementing it. After decrementing it, we are getting the value inside the D register, and after that we are selecting this variable foo.arg2, and inside that variable we are storing the value which we popped from the top of the stack. Okay, so I think this is it for push and pop of static. So let's copy this code from push push static Just need to change this. Okay, after that we need to get this pop. We'll have pop static. Right, we have the assembly code for static. After that we have temp and pointer. So this is pseudocode for push and pop temp, and this is almost similar to this 4 segments. The only thing we need to change is this. So I'll copy the code from this segment. I copy the pop instructions as well. Push 10, pop 10. Okay, let's see how can do this now. This step will remain same, arg2 d is equal to a, but this step m is equal to d. Okay, this step will also remain same, but instead of selecting any register, we'll do at 5. Store this value inside the data register. After that we'll select this address and do m is equal to m plus d. Okay, so this is and the remaining steps will remain same, I guess. Yeah, the steps will remain same. We'll do the same thing for pop. In this case also, instead of selecting a particular pointer, we'll store this, we'll store 5, and inside data register we'll store a value. After that select address, we'll do m is equal to n minus m plus d. Okay, this is correct. After that I decrement the stack pointer. Okay, the steps will remain same. So I will just copy this code and paste it over here. I will change this to push temp. And what did we change? We changed this thing to 5. Oops. and M2 A. Everything else remains same. And this also 5 and 8. Now we have the instructions for temp as well. Still need to change this name temp. Which one is next? Yeah, we have pointer. This is the pseudocode for pointer. We use it for storing the base address of the segments, this and that. Okay. So okay, let's do this then. So in this case, we will have 4 kinds of pointer instructions. We'll have first push 0, push pointer 0, and push pointer 1. After that, we will have pop pointer 0 and pop pointer 1. So let's try to write it inside comment first. We'll have push pointer 0. The code will look similar to constant. So let me copy this. So now in this case, this argument 2 will not be a value, but it will select either this or that. So we'll have to, based on this argument 2, we'll have to figure out what to pass to this stack, either this or the value of that. So we'll have to write a condition, if else condition. So we'll have to use labels in this case. Let's get a label. We'll call it, we can't call it this because it's already a variable. So we'll have to call this BS. And in this case, what we'll do, we'll have to check for condition D and J E Q. So jump if equal to 0. So if this D, which contains the value of this argument 2, We will jump if it is equal to 0. And where we will jump? We'll jump to this tab, this label, this P. And what we will do here, we'll have to get the value of this P. So value of this, so we'll get this. Now this M will have the value of this. Now we can do D is equal to M. So now we have the value inside the data register. After that, we need to select the stack pointer, and A is equal to M equal to D. So this steps will remain same, and after that we need to increment the stack pointer. Okay, so up to this point it remains same. But if this condition is not true, then inside the stack pointer we need to store that value. Wait, let me try to use a different variable. We'll call it val, and inside it we'll store one. We can do this M is equal to 1. So this val variable will have 1 by default. But if this is equal to 0, D is equal to 0, then inside P, what we'll do is first select this data, this, and we select the D. Instead of doing this, let's copy it over here, and let me copy this. Let's select that. We'll store it inside D register. After that, we'll do M is equal to D. So now this val will contain the value of that. Or else in this case we'll jump to this we'll store this value inside this val. but the flow of the program is somewhat problematic. So I should create a label over here. Let's call this assignment and incremental. This is for push. Let's just call it assign. Continue. Yeah, this will be better. Continue. And over here I'll select this continue and unconditionally jump there so that this part doesn't get this part doesn't get executed. And this is what we need to do. We need to select stack pointer, do is equal to m, wait, you know what, we don't even need this val variable. Because this d value will have the value of this and that anyway, so we can directly do this d at a equal to m and m equal to d also. So let me try to walk through it again. So first we'll select this argument 0 and store it inside the data register, d is equal to a. Now we'll select this at this p and we'll check if this d is 0. If it is 0, then we'll jump to this p label. We'll jump over here, and after that we'll select this at this pointer and store its value inside d data register, and we'll continue. We'll select the stack pointer, and inside this stack top of the stack we'll store this d value of d. After that we will increment the stack pointer. Now if this condition is false, then we'll continue with this statements. Select that and store its value inside d, and select continue and jump unconditionally to continue. And here we'll store this d value which contains this in this case. So this is the assembly code for push pointer 0. Not just 0, we have implemented for 0, both 0 and 1. This will work for both 0 and 1. Well, we could have written different code for this and that. See, there are two things we can do. Either we can write this code where we check the if else condition based on this argument 2, or we write different assembly code for both of this thing, either for 0 and 1. Okay, I think we should do that. We should write different code for 0 and 1. So if we do that, this we don't even need these conditions. We can get rid of this labels even. Yeah, I think we should do this. So if we have 0, we'll select argument 2. Wait, we don't even need to check argument 2 in this case. So we'll select this, store its value inside data register. After that, we select the stack, store this value inside the stack, top of the stack. This is for push pointer 0. And if we have push pointer 1, instead of this, we'll select that. Now let's write the code for pop pointer 0 and pop pointer 1. So we don't have pop constant, so we won't be having the code for copying. So we'll have to write it from scratch. So let's do that. Just write it down for pop pointer 0 first. So in this case, we'll first decrement the stack pointer. So we'll first select the stack pointer and decrement it. Do m is equal to m minus 1. This will decrement it. After that, we'll do a is equal to m and d is equal to m. Now we only need to do, the only thing we need to do now is store this value of d data register inside the stack. Oh wait, no. Wait, this is I think this is wrong. When we do pop pointer 0 and 1, what do we need to do? We need to pop the value of the top of the stack, store that value inside this or that. In this case, what did we do? Yeah, I think, yeah, this is right as well. Here we stored the value from that inside the on the top of the stack. So this is correct, and this is correct as well. So in this case, what we'll do is first decrement the stack pointer and get the value at the top of the stack, store it inside data register. After that, we'll select this. So we are writing the code for pop pointer 0. So in this case, we are working with this segment. Let's select this. We can directly do m is equal to d. Let's write code for pop1 as well. Pop pointer 1. In this case, you only need to change this. Instead of this, we'll select that. Alright, let's copy the code for the same. Wait, we'll have to start copying from the top. So let's create a variable for push point 0, push pointer 0. Push point 1. We only need to change this thing. What the heck am I doing? We need to change this to that. Now we need pop point 0. So let's copy the code for the same. Pop point 1. Change this to that. Okay, so let's write the condition for the same as well. The argument is pointer, argument 1 is pointer, and argument 2 is 0. In this case, oh wait, I think we might have problem. We have got it backward. So this argument 1 contains the push yeah, everything is right. We just need to change this arg2 to type parser.type. Have to change this. Argument 2 should be parser dot type. Yes, yes. And she push. Push should be changed to say push. C pop. Right. Now in this case, in case of pointer, we also need a third condition. Third condition will be if and arg2 equal to 0. So in this case, we need to do push point 0 . So let me remove this. Let's not remove it. Pointer pop weight. If it is argument 1 is pointer, type is push, and argument 2 is 1. In this case, we need to do push point 1. And if argument 1 is pointer, parser type is equal to, well, if it is cpop and arg2 equal to 0. In this case, we need to do pop point 0. And if it is 1, this should be 1. Right. We've taken care of all the cases. So in case of pointer, we have 4 different assembly combo of assembly code. Point 0, push point 0, push point 1, pop point 0, pop point 1. So we have push point 0, push point 1, pop point 0, pop point 1. Okay. What else do we have? We have, all right, so that was the last one. We are taken care of all the memory segment instructions, all the push and pop instructions. So we have taken care of the logical and arithmetic instruction as well the memory segment instruction. So now that we have done this, we need to test the sample program. P dot type equal to C push or P dot type equal to C pop. In this case, we need to call code write. What was the name? Write push pop, I guess. Write push pop, and we need to pass the parser. Let me check it. Write push. Yeah, it is write push pop, and we are passing the parser. So now we need to check if this program works or not. Oops, what happened? Expected an indented block. Oh, don't give me this error. I hate indentation errors. Oh yeah, it's because of this. I need to get rid of it. Invalid syntax. Why is it? Where is this? An invalid syntax. Okay. Instead of else, I need to use elif. List index out of range. Okay, I'm not passing anything. What do I need to pass? Simple add. Simple add. Stack arithmetic, simple add. Wait, I will be right back. I need to test VM code which contains only, let's see, which contains only the logical arithmetic and the memory segment commands. For each program, 4 files. File contains the program's VM code. vme.test script running the program on the supplied VM. To experiment the program's intended operation after translating the program using your VM translators, the supplied test script and compare file will allow testing the translated assembly code on the supplied CPU emulator. Okay, so these programs are for testing the arithmetic commands and these programs for testing the memory access command. So, well, before we get the outputs, let's write this output file command. So I'm going to get rid of this comments right now. Well, instead of getting rid of it, let me copy it inside a different file. I'll call it vm logic.txt. Let's open VM translator. Let's copy this command. Let's copy the whole of it. And paste it over here. Okay. Now let's get rid of now we can remove this comments. Okay, so now the file looks cleaner. So we're trying to write a write file. So to write to a file, first we need to open it for writing. So, oh wait, what the heck? Okay, so I was saying we need to open the file for writing first. So instead of opening it up in init function, we should directly open it up in this method, write arithmetic, because we'll have this ASM in this case. So let's delete this command from here and we should paste it over here. We have opened it up as .asm. This ASM will be the output file of our assembly code. And instead of printing, this time we'll write the output directly inside this ASM. How do I write to a file? F.write. Okay, let's see what we will write. Instead of printing, we'll do asm dot write. So where was I? Write arithmetic. Right. I need to copy this, paste, and change this print through asm dot write. Same over here as well. asm dot write. Well, you know what, let me just replace this print statement. It will be much easier. So I'm going to replace print with asm write. I don't want to manually change. So we'll replace print with asm dot write. Let's get rid of this print statement. Okay, and before we write the instructions, we'll also write commands as well. So to write command, we'll do asm.write it will be easier to so what we'll write, we'll write a command, and this command will contain the VM code for which we have written the assembly code, so that it will be easier to debug. So where's our VM code? It is inside the instruction, so we can use the parser p.inst will have the instruction. Let's keep a new line character as well. So now before let me check, we do have instruction inside the parser, so this will work. Let's try to test this program. Okay, but before that, what do we need to do? I guess this is it. Oh wait, I forgot something. I need to open the file for writing in this method as well. I forgot. And I probably need to change the flag as well. So first indent this. Okay, so let's see if I open it up with W, will create a file if the specified file does not exist. Will create a file if the specified file does not exist. But if I open it up with W, it will replace the content, which we don't want to replace. We need to append the content. But here's the thing, we do need to replace the content if we are starting the parsing from the initial stage. So how are we going to do this? So I guess in this case we need to get rid of this with clause, and we need to handle the opening and closing by ourselves so that we get the variable. So this is what I will do. We won't be using this. Use let's call it out file. let's just call it file or ASM. And this is what we'll initialize. Self.asm. Let's get rid of self pass. So this is what we do when we initialize the code writer. We'll open up a file for writing, and when we call this write arithmetic, instead of opening this thing here, get rid of it. And we also need to re-indent this code. Okay, so now it is properly indented, and we also need to change this ASM to self.asm. We also need to re-indent this lines to this if condition, and let's get rid of this line, and we need to close this file as well after we are done writing the code. So we'll write a method finish, call it finish, and this function will close the file which we opened earlier. We'll close it over here, self.asm.close. So now all we need to do is, after we are done writing the code, the file, we need to close the file. We will do this after all the instructions are done. So we'll call, so we need to get this code here. We'll call code.finish. Finish writing up. Let's hope this works. So first we'll check this simple add program. So let's see where it is. The stack arithmetic simple add. So inside simple add we have compare, test, VM, test, and output. What is the difference between this VME and just this test? Okay, let's just run the translator. We'll pass stack arithmetic simple add, and we'll pass this VM. P is not defined. Where is it not defined? Why the heck is it not defined? The error is on the line 172 and 72. Wait, why is it not defined? Previously it was running all right. Okay, wait. All right, I see. Instead of P, I have to write P parser. I need to replace this. Parser dot instead of P dot inst. Now it will work. Okay, it did work. So let's check if we have the output. Yeah, so where is it? We have the ASM file. Let's check what it looks like. That long. So for add, we have this code. Wait, why do we have the code for add only? Get stack arithmetic simple add dot bm. We have push and push operations as well, but we don't have the output for push. So where's the bug? Yeah, we are calling code writer dot code dot push right pop. So if type is C push and C pop, so either this function is not being called or this condition is not. So it happens, or might happen when the condition is not satisfied. That means there's a problem in the parser somewhere. So it might be they are not even writing anything. They're just returning maybe. Let's check if this function is even getting called. So I will log push pop called. There's no log. That means the function is not getting called. Why is it not getting called? Maybe it is returning because of this condition. So to check that, let's print some one push pop called. Yeah, it was called. So that means our function is returning from this condition. So if parser.type not equal to push cpush or cput pop, then return. Oh, but the instructions are of type cpush and cpop. Then why are they getting returned? Let's print parser dot inst and parser dot type. So this is the instruction and this is the type cpush. What the heck? Parser.type not equal to cpush. It is equal to cpush. Oh, I see. Okay. A parser.type not equal to cpush and not equal to cpop. A silly mistake. Yeah, this time I think we'll get correct output. So if we check the assembly, wait, where's the output? Even though the function is getting called, we are not getting the output. So that means we also have an error in these conditions. So let's see what is happening. Let's print arg1, arg1, arg2, arg2. Arg1 is constant, arg2 is 7, arg1 is constant, arg2 is 8. Wait, where's the line of code for constant? You didn't even write the condition for constant. Wait, we skipped it. So did we write all the conditions? We wrote the condition for this and that, and after that we directly wrote the conditions for the pointer. Wait, where are all the this, that, and pointer? Where are the conditions for static, temp, and constant? We forgot. Oh, wait. We didn't even write the conditions for constant, static, and temp. How did we forget it? Or did I overwrite something else? Doesn't matter, let's write it right now. So first we'll write the condition for constant. So if argument 1 is constant and parser dot type, in case of constant will only have push type. What do we call? We call push const. That's the name of the string, right? Push const. After that we have static, push static and pop static, push temp and pop push temp. Shouldn't this be popped temp? What the heck happened? Why do I have two temps? I didn't change these commands, they are similar. Oh wait, did I mess up somewhere when I was trying to refactor the code? Wait, in case of push and pop temp, we do need two types. The heck did I do? Push static. Okay, so I will need to copy this code now. I'm glad I saved the notes. What did I call logic? I will need to copy the logic for temp. Push temp. Yeah, we already have push temp. This is the string for pop 10. So now we need to write the condition for push pop static and push pop 10. We'll write it after constant. Static push static pop will call pop static, and we need the same conditions for temp push temp pop temp. Okay, let's see if it works now. Okay, so now this time we are getting the output, but why are we getting this empty lines? Let me check. Yeah, we don't have the empty lines. It was just the less was showing us that there are empty lines. Oh wait, this is problematic. Where are we not passing the new line character? Oh, I see. Well, let's just add a new line over here, it doesn't matter. Or no, we should have a new line here. We can do well, what if we add a new line after this? We can't do that. Now what the hell, let me just add a new line character after this, right? And let's add two new line characters. Okay, so now we need to check if this assembly code is correct or not. So to check, we'll have to open the CPU emulator. Project 7, stack arithmetic, simple add tst. This will load output file and assembly as well. What does this program do? It adds two constant on the top on the stack and adds them up. How do we know if this worked or not? So 257 is the address of the stack, so let's go to that address. 257, we have 8 on the top of the stack. So I suppose we are adding, let's try to run through the program step by step. Initializing the stack pointer 256. So let's go to the 256th address. We right now have 15 at the top of the stack, which is just a garbage value. So now we add seven on the top of the stack. After that, we increment the stack pointer, store 8 there. Let's check. So now we have 8 on the top of the stack pointer. So we add 7 and 8. So when this program is done running, we should have 15 on the top of the stack. Yeah, we have 15 on the top of the stack. So that means our implementation is correct for arithmetic and push operations. Getting correct output. Now let's try to test this program, stack test. Stack test.vm. There's a lot of code. Okay, we have the output assembly file. Now we'll try to load this assembly. Simple stack test.txt. So what this script will do, execute a sequence of arithmetic and logical operations on the stack. Okay, how are we going to know if this works or not? Yes, for that first we'll have to open the VM. VM emulator. We first have to check what this program does. So we'll open up this VM script. This is for simple add stack test VM. Now we need to step through the program. We have initialized the stack pointer. And we have pushed the constant value 17 on the top of the stack. We push 17 again and we check the equal to. What this should do is, yeah, it is returning -1. Why is it returning -1? Yeah, because let's check what it gives in this case. Pushing 17, pushing 16, and it is returning 0 in this case. So when the equal to condition is not satisfied, it is returning 0. So I guess -1 is for false and 0 is, wait, 1 -1 is for true and 0 is for false. And in our implementation we have done something different, so I will have to change that. Push 16, push 17, and check the equality. Again we get 0. 892, 88891. Then we check the less than. So 892 is not less than 891. That means we will have 0 at 259. Yeah. -1. 899, 891 will again have 0 in this case, because it is not less than push 32767 32766 and greater than. So we'll have again have 3267 and yeah, it was greater than. Seven six six greater than 0. 57 31 53, and now we try to add the 2. That means we'll have 331 plus 53, and the result will be on 266. Yeah, so the result is 84. Now we push 112. When we subtract, that means we'll have negative result on 266, which we have. After we'll negate the 250, 260, 266. So we have the positive result. After that we'll do the AND. So AND of 28 plus 57. Wait, what? Why did we get 24? So we need to do the same thing in case of the condition being false. We have to store 0, and if the condition is true, we have to store all ones. That's what we need to change in our script. What are we really doing? This is just a parser, and this is the code. Let's just check for greater than. So we'll have to check the nodes. Less than. So first we decrement the stack pointer. Wait, why do we decrement the stack pointer? Yeah, that's correct. And we get the value inside the data register. After that we decrement the stack pointer again and compare that value with subtract that value from the value from the data register and check if it is less than 0. If it is less than 0, that means the condition is true, we are storing 1, and if it is not, then we are storing 0. Wait, yeah, so we are doing exactly the same thing as they are doing. So I think this will work. This is the CPU emulator. So let's load the script of stack test. So first we are storing the value 17 on top of the stack. Okay, not stack, inside the data register. After that we are going to store that value, push that value on the top of the stack. Okay, we have that value on the top of the stack, and now we are going to increment the stack pointer. Now we get 17, store it inside data register. After that we again select the stack pointer, and at on the top of the stack we store 17, and we increment the stack pointer. After that we again select the stack pointer, decrement the stack pointer, select the store its value inside the data register. Now select the variables where we will be storing the value of y. So at 16 we'll store this value from the data register. Okay, so we have 16 inside D. Now we again select the stack pointer, decrement it, and store its value inside D. Now we again select 17 variable. That means we are going to store the second value there. Now we select 16 and we do D is equal to T minus M. So this data D will have 0 after this step. Yeah. We are doing this D is equal to T minus. Now we are selecting LT, which is the label. The heck happened? So we have selected the label and we'll check if D is equal to 0 or not. Yeah, we are jumping to this 109 now because it was equal to 0. Now we again select the stack pointer, is equal to M is equal to 1. We'll store 1 on the top of the stack. After that we increment the stack pointer. Oh wait, what is this line of code now? Where did it come from? Of course, this is the program. We also have other expressions as well. So that means this is working correctly, but in this case we are storing 0. Now after that what did we have? We have 17 and 16, and we will select the equality. So we are selecting at 892. What is this for? Push constant 17. Why is it 892? Shouldn't it be 17? Okay, I think we have a bug. Let's check the output. This is the code for push 17, push constant 17 and equality. And after that, this is the code for, wait, then why are we getting 892 over here? Okay, I see. All right. I messed it up. I wonder where else did I. So I can't directly pass this argument to. Okay, I will have to change each and every instructions. I can't directly pass argument to like this. Why can't I? Well, I can. Why can't I do that? And why am I getting 892 in this case? Shouldn't it be 17? In fact, here also I have 17. Why is this CPU emulator showing me that it is 892? Let's roll with it. Let's see what happens. Yeah, we increment the stack pointer, and after that, oh wait, where did this line of code came from? Okay, at 891, but at stake pointer is 89258. Let's check the stack pointer. We have 0 on top of. Now we have 891. stack pointer we decremented and store value inside D register. Jump if less than, so it is not less than, that means we'll jump to 2. Oh wait, yeah, of course it is not less than 0. Wait, why do we have a less than jump? Which condition is it? Checking. And we are checking for equality. Where did this less than come from? Let me try to reload the program again. Should look similar to this code. Wait, I guess it is same now. Or is it? Let's see. Up to this m+1, it is for push constant 17. Up to this m+1, push constant 17 again. And after that, the equality starts and it will go up to m+1, m is equal to m+1. So this to JEQ, we have JEQ. M is equal to m+1. Now we have this instruction, which is this one, 17 D is equal to A to m+1. After that we push 16. Okay, so yeah, it is correct. Previously I think I didn't load the file correctly, so let's try to walk through the program again now. Alright, we have loaded two values, 17 and 17, on top of the stack. Where did this 892 came from? Okay, I see what might be happening. We are also changing the values of this program. So see, right now we don't have those. Wait, we do have. Let's try to load the program again. Wait, the values are here. Why did I miss them previously? One loading 17 and after 16 0. Well, yeah, it is correct. Okay, these are these values. I think I am just getting confused. That's why it's hard to walk through the program step by step. I think I will try to test this program again in the next stream. I still haven't had my lunch. So guys, I'm gonna take a break now and I will see you guys soon. Bye bye.